We have learned about balancing chemical reactions and mole calculations. We can dive into stoichiometry. Now, stoichiometry is the use of balanced chemical equations to answer questions like how much? How much of this reactant will react with how much of this reactant to provide how much of this product? So that is stoichiometry. Basically the mathematics of chemical reactions. So the coefficients in a chemical reaction, remember those coefficients balance the chemical equation, represents the moles of each reactant or product involved in that chemical reaction. So we can use these coefficients, we can use the moles of each reactant or product to create conversion factors or any relationship within that entire chemical reaction. So let's look at an example. If I were to read this reaction, I would read it as hydrogen gas reacts with oxygen gas to yield water or water vapor, depending on the temperature of the reaction. Now, the first thing I need to look for is, do I have a balanced chemical equation? Well, I notice that I have two hydrogen on my reactant side and two hydrogen on my product side. So that looks good. However, I have two oxygen on my reactant side, but only one oxygen on my product side. So I'm going to have to balance this chemical reaction first. In order to do that, I'm going to balance my oxygen by putting a 2 in front of the water. However, now I have four hydrogens in my product side, so I need to put a 2 in front of my hydrogen in order to make it make the hydrogen balanced. So now that I have a balanced chemical reaction, I can read this as two hydrogen or 2 moles of hydrogen react with 1 mole of oxygen to yield 2 moles of water. So let's get all of the conversion factors from this problem. So I can use that coefficient, the 2 in front of hydrogen, and I can write it as 2 moles of hydrogen. And if I wanted to create a relationship between the hydrogen and the oxygen, then I would just use the coefficient of oxygen and write 1 mole of oxygen. So the relationship between hydrogen and oxygen is 2 to 1. Now I can also make the relationship between hydrogen and water. And then finally, I can make the relationship between oxygen, 1 mole of oxygen, and water, 2 moles of water. Now, what I want you to remember is that if I have one conversion factor, the reciprocal is also true. So for every conversion factor or for every equality, remember these come from equality statements that 2 moles of hydrogen is going to be equal to 1 mole of oxygen. So for every equality statement, I can get two conversion factors. So the other conversion factor for the relationship between hydrogen and oxygen is going to be 1 mole oxygen over 2 moles hydrogen. And I can do the same thing with my next relationship. And then finally, the relationship between oxygen and water. So remember, when we are comparing two different substances, I cannot compare the grams of those substances because they have different masses. There's different amounts. I can only compare the moles of those different substances. That's why this multiple ratio is so handy because we can convert between two different substances. So let's see how we can do that with our chemical reactions. So here is a reaction between potassium nitrate, carbon, sulfur, and to produce carbon dioxide, carbon monoxide, nitrogen, potassium carbonate, and potassium sulfide. Oof, that is a lot of stuff going on. So the first thing I look at is my chemical equation balanced? And it is. I already see the coefficients out in front. I can go through and make sure that the coefficients are correct just to double check. I can then look at my problem. How many moles of nitrogen gas will be created if 2.50 moles of potassium nitrate completely react? Something I want to point out to you is I am only concerned with potassium nitrate and nitrogen gas. So for this problem, those are the only two things that I am going to be looking at. So I can look at my chemical reaction and find those two substances. So for this problem, I'm not going to concern myself with any other substance in this chemical reaction because the problem is only asking about those two things. So the only relationship I'm going to need is between those two things. When we do this, I notice I'm going to set this up exactly like my conversion factor problems. I'm going to state my given. It's the only number provided, 2.50 moles of potassium nitrate. And I'm going to state my need. How many moles of nitrogen gas? So I'm going to need moles of nitrogen gas. Remember, nitrogen is a diatomic element, so nitrogen is N2. When you are converting between two different substances, the only way to do that is with the mole to mole ratio. So I need to look at the coefficients between the two things that I'm interested. What is the relationship between the two substances, my given and my need? And that is how I will get my conversion factor. So I have 4 moles of potassium nitrate, and that is going to be equal to 2 moles of nitrogen gas. I can start my problem. Notice how I just wrote this as an equality. I didn't write it as a conversion factor because I don't know what I need on top and what I need on bottom until I actually start my problem. So I'll start with my given, 2.50 moles of KNO3 times. In this conversion factor, I have to have moles of KNO3 on the bottom so it will cancel out. So that tells me that my 4 moles of KNO3 are going to be on the bottom, and then my 2 moles of N2 will be on the top. When we plug this into our calculators, we'll take the 2.5 and multiply it by 2, get that answer, and then divide it by 4. So you multiply everything across the top and then divide it by everything across the bottom, and we should get 1.25 moles of nitrogen gas. So another way of reading this would be if 2.5 moles of potassium nitrate react according to this equation, then 1.25 moles of nitrogen will be formed. I want to point this out to you. In order to get from moles of one substance to moles of another substance, you need to use the reaction coefficients. And this is referred to as the mole to mole ratio. Well, we can take this one step further because when we go into a lab, we're not usually measuring out the moles of substances. We don't have balances that measure out the moles of substances. We have we have balances that measure out the grams of substances. So we can use stoichiometry to answer these types of questions. How many grams of products can be obtained from a certain mass of reactant? And in stoichiometry, A and B are used to describe what it is that you're converting between. We can also look at how many grams of reactant are needed to produce a given amount of product. Now, A is always what is given, B is always what you want to know. So it doesn't matter if they're reactants or products. So don't get confused by that. But if you start with grams and you need grams, then you will always follow this pathway. You'll start with grams of A, and in order to get it so that you can make the comparison between A and B, then you have to get it into moles of A. And to do that, you use the molar mass. Well, as soon as you're in moles, then you can use those reaction coefficients. You can use the mole to mole ratio in order to convert into moles of B. Once you're in moles of B, you simply use the molar mass of B in order to get 2 grams of B. Whew, that was a lot. Don't be alarmed if you did not follow along with that at all. So let's put some numbers to this and some actual molecules or compounds instead of using A or B. Here is a chemical equation right here. Arsenic compounds have been used as poisons for most of recorded history. One method for detection of arsenic is called the Marsh test. It was based upon the production of arsine gas through the following reaction. So here is our balanced chemical reaction. Calculate the mass of water produced in the Marsh test, assuming the reaction consumes 2.72 grams of As2O3. I'm going to set this up exactly like all of my conversion factors. My given is going to be the number 2.72 grams of As2O3. My need is going to be in the form of a question or a bossy statement. And in this case, it's going to be the bossy statement. Calculate the mass of water. So mass is units of grams. So I'm going to need grams of water. And as soon as I write this out, I can easily see that I'm going between two different substances. So that's going to trigger in my brain that I need my mole to mole ratio. When I look at my balanced equation, I'm only going to concern myself with the substances that are in my problem. So I'm only going to look at As2O3 and water. I don't care about my other reactant and my other product for this problem because the problem's not asking about it. So when I look at my mole to mole ratio, I'm just going to look at 1 mole diarsenic trioxide is going to be equal to 3 moles of H2O. I don't have all the conversion factors that I need yet, but I'm just going to get started. I'm going to start with my given. And I know I'm going to need grams of As2O3 on the bottom with my first conversion factor. Can I use my equality yet? No, I can't because I'm in grams and my equality is in moles. So I have to first change grams into moles. And how do we do that? You got it, molar mass. So I'm going to have to calculate the molar mass of As2O3. You can go ahead and pause the video while you go through and do that calculation. All right, what did you get? I got 197.84 grams of As2O3. That's taking the mass of As, multiplying it by 2, and the mass of oxygen, multiplying it by 3, then adding those two together. And this is going to be equal to 1 mole of my diarsenic dioxide. As you can see, my grams cancel, and now I am in moles. Well, that's good because now I can use my mole to mole ratio. When I'm writing out my mole to mole ratio, I have to have moles of the As2O3 on the bottom so that I can cancel them out. So when I fill in my conversion factor based on my mole to mole equality statement, I'm going to put 1 mole right here for the As2O3 and 3 moles of H2O. Now my moles of As2O3 cancel out. Well, I've converted to water, which is good because that's my need, but I notice my units are not right. I'm now in moles of water, but I need grams of water. So I can't just magically change this to grams. That's not how this works. I have to convert moles of water to grams of water, and you got it. We need to use the molar mass of water. So I'm going to calculate the molar mass of water, 18.02 grams of water per mole. And notice our moles of water cancel out, and I am left with grams of water, which is good because that is what my need is. All right, let's calculate this out. When you plug this into your calculator, you will plug in 2.72 times 3 times 18.02 and then get that answer and divide it by 197.84. So go ahead, plug that into your calculator, come back, and we can give our answers together. Okay, what did you all get? I get 0.743 grams of water. That is stoichiometry right there, using the multiple ratio as a conversion factor between two different substances, and then using the molar masses of those substances in order to get to units that we can actually use in lab. Now, chemical reactions do not happen perfectly. So if I do this reaction and I have 2.72 grams of my diarsenic trioxide, then theoretically I can form 0.743 grams of water. So this is in a perfect world, in perfect lab conditions where there are no competing reactions. This is how much water I can get. Now, in the previous problem, we looked at only one reactant. We didn't look at how much hydrogen we had, but you have to have both of these in order for a reaction to take place. So the limiting reactant in a chemical reaction is the reactant that is completely consumed. Another way of thinking about this is it runs out first. It runs out first. So if you completely run out of one reactant, then the reaction is going to stop. So when the limiting reactant is consumed, the reaction stops. It limits the amount of product that you can make. One way to think about this is just in any reaction that you do in your life, whether it be making a sandwich. How many pieces of bread do you have? How many pieces of meat do you have? Or when you're making a s'more, how many graham crackers? How many marshmallows? How many pieces of chocolate? As soon as one of those runs out, you cannot make any more s'mores. That is going to limit the number of s'mores you can make. The same is true with a chemical reaction. As soon as my limiting reactant runs out, I can't make any more products. So the maximum amount of product that you can make, that is called the theoretical yield. And that is what we calculated here. In our perfect world, where there were no competing reactions, if we may started off with this much reactant, then theoretically, this is how much product I can get. When you're doing these types of calculations, it's really convenient to look at the how efficient a chemical reaction is. So we can do that by calculating what is called the percent yield. And the percent yield is a way to compare, it compares the theoretical yield and what actually happens when the experiment or when the reaction is performed. So to do this calculation, you would just calculate the percent yield by taking the actual yield and dividing it by the theoretical yield times 100. So the actual yield is exactly what it sounds like. It's what you actually get when you perform this reaction.